it's 10 past. I think this is about it, so I'll start. The topic of this talk is OpenJDK under the hood, so we're going to look inside OpenJDK. I want it to be as interactive as possible. If you have any questions at any time, please ask, and we'll go into things in more detail. If I feel we're deep diving a bit, I may ask you to come and talk to me later. Okay? Okay, so we're going to look at these topics, and some of them are very simple. Where do I get it? How do I build and install it? What secret options are there? There's loads of secret options you can use. A quick look at the source tree, so if you're not familiar, how you find your way about it. And then a look at what happens, how you get from your Java source code to machine code. And that essentially involves looking at these three items: the template interpreter, the C1 compiler, and C2 compiler. And then we're going to have a look at the optimizations we have been performing on OpenJDK over the past year. So, where do I get OpenJDK? Well, unfortunately, there are lots of different places to get OpenJDK. It's a bit fragmented. The easiest place is probably just to get it from your distro. Okay? If you have a standard Ubuntu or Fedora, you can get the source package just by doing apt-get source. Actually, you need to get source OpenJDK-7. That's missing there. And you can go away and grab OpenJDK, and then cd into that directory and do package build package, and then that will download all the dependencies you need for that, and then it will actually, it doesn't tell you if they're on dependencies. You have to manually download them, and then you can just build the package. Very simple. Or the other place you can get it is you can go to the upstream. So for JDK 7, the upstream is this project called ICT. You'll also find JDK 7 in the main repository in OpenJDK java.net. But the thing is, the distros generally take it from ICT rather than OpenJDK. And the reason for that is partly historical. When the OpenJDK was made open source in, I think, about 2006, was it? Maybe 2008. It wasn't in a state that could be used in open source. There were still a lot of binary plugs that needed to be used with OpenJDK, and the ICT project was set up by Red Hat to resolve those binary plugs and make it completely open source, and also to provide a distro-friendly build architecture, because the build in OpenJDK 7 was a bit arcane, whereas ICT has a standard configure and make that is familiar to all distros. So ICT provides your standard configure and make, and it also provides within the ICT force a clone of the upstream JDK with many additions inside that, for example, the ARM microchip and also the ARM port. Okay, as I mentioned, it's a forest, so within that you've got these six repositories for OpenJDK, so you also have to get all of those, which can be a bit of a pain, but there's a handy script within I don't know, do you refer to it was the head or the root of a forest? So you can just execute the get source script and it will clone all the sub-repositories. So like this. If you just want to do a one-off build, you can just download a tarball rather than using your material to clone the sources. So this, if you pull this source tarball, it doesn't actually contain the sources within that. It's just scripts that will pull in the correct tarballs for that build. And then it's just a case of doing wget that tarball, cd into ICT2.4, configure and make. So that's JDK 7. JDK 8, where do I get JDK 8? And I'm talking specifically about AR64. At the moment, JDK 8 unfortunately is on a branch in the OpenJDK repository. It is unlikely that that will ever be merged back into the main repository because the JDK 8 is now a closed project. Development is complete on that, so they won't accept any further changes, which unfortunately means that for the foreseeable future, distros will have to go to a separate branch to build for AR64. Within JDK, there are 7 subtrees, so the alert amongst you will notice the additional one is this mouse line, which is the JavaScript. Okay, as with JDK 7, you can just use the get source script within there to pull down all the additional repositories. Cross-compilation of JDK 8 is supported, so there are 2 scripts within there, there's cross-configure and cross-compile. Obviously, if you want to cross-configure, you need all the cross-compilers and etc. And those can be produced as a byproduct of the Open Embedded Lake Java build. Now that can be quite tricky to build and takes 3 to 4 hours to build on a reasonable performance PC. So I've conveniently just put one here at this URL, so you can just download that, install it, and then use that to support cross-compilation. There's also this support for something called the built-in simulator. Okay, so the built-in simulator is a very small simulator written in C with a little bit of assembler. The idea is that simulator is linked against Java. Okay, so if you're building on x86, you build the whole image for x86, and then when it JITs the code, it JITs ARM64 code, and then when it calls the ARM64 code, it calls the trampoline function, which enters the simulator, and that simulates the ARM code. Then if that ARM code makes a call out to the runtime, there's another trampoline function which calls the x86 code. And this is very convenient for rapid development of code, because it means you can just run everything on our PC and make changes to the JIT without having to copy it over onto a board somewhere in the lab and copy that. Okay. The source code of that simulator is available on SourceForge at that URL. If you just run this script, it will automatically download the source as part of the build. JDK9, well, JDK9, where do we get that? From the trunk. So with JDK9, we've merged it into the trunk, so you can now pull down the trunk and you get the pull down AR64. So this is great. And the upside of it means, we're always up to date with all the developments in Java, and security patches are immediately available for AR64. There's a single code base for distros. Downsides are the usual downsides with working upstream, no support for the built-in sim, so you can't have your own proprietary stuff in there. Cross-compilation is not really supported, so you can make it work by copying over the patches from JDK 8. The client build, you can't build the client out of the box. Then you have to put in some additional patches to make that work. And there's an additional level of bureaucracy once you're working upstream. Every change you make, you have to file a bug report, no matter how small it is, and then you have to push your patches for comment against that report, get them approved, but the advantages of being upstream far outweigh any disadvantages. Okay, so that's where I get it. How do I build it? Okay. First time I started working with OpenJDK, it was horrible. I spent about 3 weeks just trying to get this thing to build, and I thought I was going to. So I put together some building instructions here at OpenJDK.Linaro.org, and it just talks you through the basic steps, what packages you need, etc. The first thing you need to build OpenJDK is you need a working Java. It's just like GCC. In order to build GCC, you need GCC. And the rule is that you must have an up-to-date version of OpenJDK. It must be at most one version older than the one you're trying to build. So for JDK 8, you need either JDK 7 or previous build of JDK, build of JDK 8. So if you want to start that, you need to get a binary. Go to OpenJDK.Linaro or put down binaries for JDK 7, 8, or 9. If you're starting off for the first time on a system, you don't have a port, you either need to build using post compilation, or you can use something called ECJ, the Eclipse compiler for Java, and that can be used to build your first system and bootstrap that way. Standard build for JDK 7, 8, and 9 is just configure and make, or for 8 and 9, just make images. However, the scripts are completely different for IST and JDK and JDK 9. So configure help will tell you what the options are. The first thing you must do is tell it what JDK to build against, what JDK to use as the bootstrap. So for IST, we tell it JDK home is location of where you downloaded it. For JDK 9 is which boot JDK. If you don't specify these options, it'll try and make its best guess as to where they're installed in usual places, but sometimes it doesn't find them. Okay, if you're building JDK 7 from material rather than a tarball, there's one extra step before you do your configure and make. You have to run OpenJDK to generate all the files. Okay, as I said, IST automatically downloads all the sources it needs to build, which, if you're trying to do some hacking, can be a problem, because you're obviously trying to change the sources, and if it detects that they've changed, they just download a new copy. So use the OpenJDK source here to point to your set of sources, and it'll stop downloading sources. Okay, so just like this. And never put your source tree inside the build directory, because if you do make clean, it takes your source tree away. You only do that once. JDK 8 and 9 builds maintain a number of different configurations within the build directory. So you can have builds for debug or release for client or server, or even for different architectures. So just a recent look inside the build directory, I have builds for AR64 and x86, server release and server slow debug. Names them all like this. And then if you want to build one, you just must set the config variable to point to the correct one. So conf equals whichever one you want to build. Make images will make, in this case, the server release. Lots of options to configure, both in IST and OpenJDK. So here are some more useful ones. Enable 0 enables the pure C interpreter. So that's useful if you've broken the build, broken the JIT, you need to go back to build the C interpreter so that you can bootstrap again. Disable docs, just don't generate the documentations, speed up the build. Disable hotspot testing build. By default, the hotspot does a self-test during the build, and sometimes if you're working on broken things, that can cause the build to fall over, and you can no longer build it, so just turn it off with that. You can also select whether you want system libraries or whether you want to use these built-in libraries. And that depends. Sometimes it's useful to build these in if you want the distribution to be more portable across different systems. So if you want the same binary to run on, say, Red Hat, Ubuntu, and Debian, you can use the built-in libraries, and that makes it work a bit better across distros. But generally, the best way for it to work on an individual distro is to build it on that distro itself. That's the only way you can guarantee it will work on that distro. Parallel jobs equals n, do as it says. Disable bootstrap, so it just doesn't do two-stage bootstrap building, speeds up the build, and with jar it goes fast jar. The standard jar is very slow. There's a protocol fast jar inside which will again speed up the build. Standard build on an ARM64 system takes about 30 minutes on a desktop PC, which is a 6-core, 4.5 gigahertz machine that takes about 8 minutes. So, JDK 9 configure options, again, as the different configures, so it's a bit of a pain moving between them. You can specify what you want to build, and you can specify a comma separated list. And so if you specify a client, comma server, it will build both client and server and merge them together into a single package, so that you can then just run java-client or java-server. Specify your debug level, release fast debug. Fast debug just means it has the assert statements in, but it's still compiled -03. Slow debug has all the asserts and debugging aids, but it's also compiled -0. With jobs again, parallel jobs. Sysroot, so if you're doing cross compilation, you can just use with Sysroot point to the Sysroot to download it. And you can switch between using which JVM interpreter you want to use, pure C++ interpreter, or if you've got a template interpreter, you can use that instead. Useful to make targets, you can make hotspot if you only want to rebuild hotspot, and log equals debug, because obviously if you're broken your make system. How do I install and run it? Well, on OpenJDK Linaro, .org, I provide a number of tarballs, and you can just download them, untar them, and run them. But you must understand that you have to have all the dependencies, and I've had quite a few bug reports that, oh, I just downloaded and untarred it and run it, and it didn't work. It got null pointer exception. It's because you haven't installed the font config packages or this sort of thing. So the best way to install it is, if your distro supports it, is just to install from that. Once you've installed from the distro will have got all the dependencies, then you can take the latest engineering release and then download that, knowing that you've got all the necessary packages installed. Two different flavors of JDK. You can download the JDK package or JRE package. If you just want to run some Java application, what you want is the JRE. If you're doing any development, you want the JDK package. Think of them as the equivalent of the normal -debug package versus the standard package. So, yes, when you install OpenJDK, you don't just get Java, you get all of these. And a lot of these are just to do with development with Java. The most interesting ones are obviously Java, run my class. Active Viewer runs a Java applet. Java C compiles your source, and Java P is a debugging disassembler for the class. All secret options are there. Okay, all secret options start with -xx, colon, and are not documented. The only place they are formally documented is in the source code. Boolean options you specify -xx plus or xx minus. Other string, its option equals value. There are a couple of attempts to list these people have made on these different websites, but the only way to find all of them is to go into the source, and they're all in files named globals of HPP. It might be globals _C2 or globals _C1, depending on whether they're C1 or C2 options. So just look at some of the options that are available. The first one is an interesting one. Unlock diagnostic VM options. So quite often you might specify one of these options and it'll say option not known. Well, it does actually know about it, but it's hiding the option until you give the xx plus unlock diagnostic VM options. I don't know why they decided to do that. Print compilation, print assembly, you can just print a line each time it compiles, or you can print the full disassembly. Use compressed loops. Okay, this is an interesting one. By default, this is on, and what it means is it stores object pointers in 32 bits instead of 64 bits. And it uses a shifting technique so that it shifts the pointer by 3. So you can address up to a heap size up to 32 gig using compressed loops. The advantage is it's just faster moving 32 bits of data at a time, and also it saves space. Once your heap size goes above 32 gig, then obviously you have to go to full size pointers. You don't have to specify the option once your heap size goes over 32 gig. If your heap size goes over 32 gig, Java will automatically detect the heap size is greater and will automatically move to 64 bit pointers. Use large pages. Okay, if your system supports large pages, you can tell Java to use those and try and allocate the large page pool. You can enable or disable the use of AES and SHA instructions. Those are cryptographic instructions in the ARM64 architecture. If they don't exist on your architecture, it will automatically detect that and not use them in any case. So this is only on systems that have those instructions. You can enable or disable bias locking. So bias locking is a form of locking where when it takes a lock, it assumes that the thread that is going to take that lock next time is the same thread. Okay, it assumes that it's just in a loop, locking something, doing something, unlocking, which is a very typical case. So when it takes the lock, after taking the lock, it doesn't bother unlocking it. It keeps the lock with that thread. So that can be a good performance improvement. The downside is obviously if you do have a genuine system where you have two threads that are competing over a lock, when the second thread comes along, it finds that the lock is marked as locked, even though it might not be locked. So it has to downgrade the lock to a full lock rather than a fast lock. So sometimes it can produce a performance benefit, sometimes it doesn't. It really depends on your application, and you need to play around with that and benchmark and find out which is the best option. Enable contended. Okay, so contended memory accesses occur when you've got a coherent memory system and you access memory locations within the same cache line. So if you imagine you have one thread which is accessing at offset 0 within the cache line, and another thread is accessing at offset 4 within the cache line. Okay, your memory system sees this as just accessing the same cache line, and therefore, even though they are separate memory locations, it can end up with contention between the different threads. The way to solve this is you can use the contended annotation, and by default, contended is enabled. And what that will tell it to do is within your class, when you use contended, it would put the two fields in separate cache lines. So it would pad the next field out to the next cache line, so you don't get memory contention like that. The good news is on ARch64, because we have a weak coherency model, you don't need this at all. So you should just turn it off. All it does is waste space within the class. OpenJDK comes with 4 different garbage collectors, and you can just enable the different garbage collectors. So you've got a G1 garbage collector, you've got the old parallel scavenge garbage collector, or the concurrent marking suite garbage collector. You've got something called thread local allocation that's on by default. So what that means is it's going to use the thread local storage when it's just allocating local data. You can disable inlining, and you can also get it to print what inlining choices it's making. Print interpreter is an interesting one. If you're looking inside OpenJDK, you can get it to disassemble the entire interpreter that it's generated and have a look at that code. On-stack replacement, okay, that's a technique where when it's executing a method and it decides that method is worth compiling, it compiles the method and then it can do an on-stack replacement, so it immediately transfers from executing that in the interpreter to executing that in just code. Whereas without that, it has to wait for that method to exit, and it's only on the next time that method is called. This is very advantageous for benchmarks, because typically what benchmarks do is they just execute continuously in a loop, and what you find without on-stack replacement, is even though you've compiled the code, because it's executing in a loop within the interpreter, it doesn't actually run your JIT code until you exit the benchmark and make it call that again. So I'm not sure how much benefit it is in real applications, because real applications usually don't sit there running in loops. So. Lots more options there. Just compilation, allocation prefetch. That's an interesting one. So what that does is when it allocates some memory, what it will do is we'll just poke several cache lines into that memory. Just do a quick read using the ARM prefetch instruction on the assumption that if you've just allocated a piece of memory, you're probably likely to start using it in the near future. So it's good to get that into cache as soon as possible. You can control the inlining, tell it what depth to inline to, and the maximum size of methods. You can tell it the maximum code size to use. You can tell it to compile a single method, or you can have a file of methods that you want compiled. You can tell it to start compiling at a particular method 1000 or whatever. Tell it to stop compiling, very useful for debugging. If you think there's a bug in a particular compiling a particular method, you can narrow it down using a binary chop. These are, again, optimization options. You can tell the compile threshold, so that tells it how many times a method is called before it's compiled. Back-edge threshold tells it how many times a loop is executed before it will compile a method. So all of these options can be used to tune your application, okay? So we provide these, and we expect then when people install a Java application that they will go through and try these different options to find the best set of options. We can't say what is the best set of options. There's no one set of options that will fit all applications. Yes, Yasin.
So I don't really have much experience with Java at this level, but you mentioned these are secret options and they're not documented.
Yes.
But is it a well-known thing amongst the Java developer community?
Yes.
So there's no.
It is.
Okay.
And people do use these when they're installing applications. If you look at Minecraft, for example, it starts up Java with a lot of these options specifying the garbage collector to use, etc. Possibly people shouldn't be using them because they're secret, but
well, they are not secret anymore, no?
Well, they've been a very badly kept secret. There's lots of people do use them, so I don't think support is going to be withdrawn because it would just cause too much pain to remove these. Tiered compilation. Okay, you can enable or disable tiered compilation. Tiered compilation is a technique where it compiles first with the template interpreter. It executes first with the template interpreter, then compiles with the C1 compiler, and then with the C2. Why would you want to do that? Well, the reason is that it uses, when it compiles with the C1, the client compiler, it installs profiling code in the C1 code it generates. It then runs with that profiling enabled, so it can work out what the control paths are through the code. And then when it comes to compile the second time with the C2 compiler, it can do a much better job of optimizing because it knows what all the control paths are. Superword optimization. Okay, superword is essentially its term for SIMD, so that's enable or disable SIMD operations. There are some superword optimizations that can be done without SIMD. For example, if you think of an AND and OR 232-bit values, that can also be done in 64-bit operations. Jump tables versus binary search for switches. Intrinsics. Okay, intrinsics are built-in methods that are recognized by Java, and you can just tell it to list those for debugging purposes. And again, some optimization options. You can tell it what the limit is for unrolling loops, and enable or disable the use of CRC32. So see, there are lots of optimization options that you can use there to tune your application. Okay, we just look through the components in the source tree. So when you download or pull Mercurial, you find there are 7 main components: Corva, JAXB, JAXWS, and elsewhere. Generally, you don't need to touch these. These are, I haven't looked inside them. They work fine. Don't need to know about them. Lang tools contains the source for all the Java tools, the Java compiler itself, the header generator, and the disassembler. The main things you're going to be interested in are the JDK itself, which is all the Java class files, and Hotspot, which is the Java execution engine. Looking inside Hotspot, we've got 3 components in there. The Hotspot serviceability agent, which is the agent that's used to connect the debuggers and profilers and things like that. The JFrag test suite is part of the source files, the regression test suite, and then Hotspot source is the main source for Hotspot. Looking further down within there, within source, you've got the shared component, which is the VM and all the tools. CPU is your CPU specific part, and that's where you find AR64, RPC, Spark, x86. Interestingly, the zero also lives in there. The zero is treated as a special class of CPU. OS specific stuff, and these are the different OSs you'll find. The only OS we support on AR64 is Linux. And OS CPU is where you'll find things that are both the OS and CPU. Okay, so looking further down within the shared code, you'll find this thing called ADLC, the Architecture Description Language Compiler. So C2 is written in this thing called an architecture description, and that's then compiled to C and C++, which is then compiled by GCC. ASM contains the assembler and macroassembler interface. C1 compiler interface. Class file is all the class file loading and verification. GC implementation, you've got 4 different GC implementations in there. Concurrent marking suite, your G1 implementation, parallel scavenge, and a new parallel scavenge. Interpreter is where the C++ and the template interpreters are found. Opto is where the C2 compiler is found, and then runtime Java runtime support. So then looking right down, here is where you finally find the AR64 port itself in source share AR64 VM, and there's about 95 source files in there that contain all the AR64. And then, interesting, I said the zero was treated as a separate class of CPU, so in exactly the same location as the AR64, you find this zero VM star, which is the zero CPU port.
So, are there any standard benchmark for us to compare performance different CPU architectures?
Yes. Okay. So standard benchmarks are Spec JVM 2008, Spec JBB 2013.
So it's not included here. It's just the sort of publicly knowledge.
I haven't really covered what benchmarks are available, but those are the 2 main ones. There's also something called Capo, which is quite used. One of the ones we use is Hadoop. We benchmark the speed of Hadoop doing a TerraSort. That's not a formal benchmark. We're just using Hadoop as an application.
Yeah, it's a complete workload. So how? What's the status now? Are we half the speed of x86?
I'm not going to go there.
Okay.
Okay, so for the next few slides, we're going to look at how Java is converted to machine code. Okay, so we use this program as an example. It's a very simple program to calculate the Fibonacci recursive. So if x equals 1 or 2, obviously the result is 1. Otherwise, it's the result of the x minus 1 is x minus 2. And here we just pull the method. We use string arg 0 to prevent the compiler from optimizing this away, because obviously if you said calculate a fixed number here, the compiler will say, yeah, I know what that is. I'll just convert your whole program into a print. So, you Java see your Java source and it generates Java bytecode, and then you can disassemble that using the Java P disassembler. So this is what Java bytecode looks like. So, it's a stack-based language. So here we've got load local variable 0, which is the argument function, iconst 1, so, and then we're going to compare against iconst 1. So looking back at our source file, if x equals 1. We're going to do exactly the same with the argument again, load it again. We have to load it each time because it's stack-based language, obviously, so when we do an iLoad onto the stack and then use it, it's popped off again. So we're comparing against 2, okay? And if it's equal to either 1 or 2, we're going to just do iconst 1 and then return. So in our source code, that's essentially that part of the code. We then get on to the next bit, so we're going to again load x onto the stack, iconst 1, isub, and invoke this method, which is itself. So essentially what we've done here is we've done that part, did x minus 1. Same thing with did x minus 2, and then we're going to add the 2 results from those and return the result. So we've basically done the add and return. So it's a very simple conversion to Java bytecode, and Java bytecode is very easy to understand. Not very efficient to execute, and obviously you can see there's lots of loading and storing onto the stack. Unfortunately, stack-based languages are not ideal, which is perhaps why we don't see them that much. So the first stage in executing this is to execute it with the template interpreter. Okay. So the template interpreter is constructed dynamically at runtime. It's not a static compiler that's built into Hotspot. So what it does is it looks at your architecture, looks at the features it has, and it can construct an interpreter that is optimized for your particular architecture. Okay. You can disassemble the whole interpreter. It's about 120K altogether. And the following is an example of the to do an IAD instruction. So very simply, it's going to load the top stack minus 1, do the add, and then it's going to exit in what's called ITOS, integer top stack state, which means it's not an integer on the top of the stack, which is in W0. Now you notice that here, even though it's 32-bit values we're dealing with, it's still using a full 8 bytes per stack element. And the reason for this is a bit historical, because originally when James Gosling designed the Java language, he defined an integer to be the same size as a pointer, which is a bit unfortunate because he didn't think that pointers might one day become bigger than integers. So now we're stuck with this situation that on the stack an integer must occupy the same space as a pointer, which can be 64 bits, to allow 64 bits. So having done the basic operation, what it's going to do is load the next bytecode from what we're using as a Java bytecode pointer. It's going to index into the ITOS table. So there's separate jump tables for each state, whether you've got an integer, a byte, a character, a pointer on the top stack. It's going to load the address of the next routine, so load into register X9. X21 is the base of all our jump tables. W9 is the bytecode we've loaded, and it's going to shift up by 3 because it's loading an 8-byte pointer, and then it's just going to branch to X9. Okay, so the top stack is hashed in the register, so it'll obviously be W0 or X0 for 32-bit or 64-bit, or S0 or D0 for floats or bubbles. And there are 9 different top stack states, 9 different types of things we can have on the top of the stack. A byte, character, short, integer, long, float, double, ATOS, this there for pointers, this actually means of an object on top of the stack. And VTOS is void, so it means there's nothing on top of the stack. Okay, this I've already said. Just looking at another one, this is the entry for icons null. So this just pushes a null value on top of the stack. And you'll notice there's 1, 2, 3, 4, 5, 6 different entry points. Whereas for IAD we didn't see this. Okay? And the reason is that when you're pushing this result onto the stack, it has to push the previous value that it's got cached in the register. But this could be cached in different registers depending on what state it's in. So obviously if it's got an integer or shorter character or a byte, it's in x0. If it's a float, it's in s0. So it has to have different entry points for each of these. So each of these just pushes the value that's cached onto the stack and then branches to the to actually do the operation, which here just moves 0 to the top of the stack because it's icons null, and it takes it's in ATOS state, which means it's got an object on the top of the stack. And then we've got exactly the same dispatch code to go in this Java Bytecode. So that's how the template interpreter works. Any questions on the template interpreter? All very silent.
So the top of the stack is kept into the register at 0 or
Yes.
0? Okay.
Yes, it's just an optimization rather than continually pushing and popping the same value off the stack. Let's hold it in a register. Another optimization I've used in the past with the ARM microJIT is to hold 2 values in 2 registers. But you do tend to get a bit of explosion in the size of your interpreter then, because then you need to have so many states, because you have got different states for it. Well, I've got 2 integers, or I've got an integer and float, and it gets very big very quickly. So Hotspot just does a single register. So as I said, the template interpreter is generated dynamically, and this is where you'll find this in the ARM's support code. So we looked at the IAD instruction, and this is then just the code that in C++ that will generate that. So it's the same code for any integer operation, IOP2, 2-operand operation. First thing it does is this transition. So it's entered in ITOS because we've got an integer on top stack on IAD, and it leaves in ITOS. Okay, it's leaving an integer on top stack. Okay. We need one additional argument off the top of the stack for the second operand, and then we just switch on the op and generate add sub whatever it is, and then at the end it's just going to return, and the caller will generate the dispatch code for the subsequent bytecodes. Okay, so this is the code that generates the dispatch. So it just does the load, and then dispatch base checks, are we using the standard interpreted dispatch table, i.e. we've got it cached in the register. It does that add we saw, and then loads the next pointer, and then branches off. So this is just dynamically generating of code that we saw earlier. Okay, the second example is just a very simple one. The code we looked at before, icons null. So this transitions from VTOS to ATOS. So we've got void on the top stack, and we're going to exit with an object on the top stack. And the code for VTOS is just 1 by 0 to 0. So here, because the transition is from VTOS to ITOS, it means icons null can be entered in any state. So that's why we saw it had to generate 6 different code sections for the state it might be entered in. Okay, because it must transition from whatever state it's entered in into VTOS, which is the expected state. Okay, so we just have a look at the C1 compiler. So the C1 compiler is contained in any source file listed, so C1 underscore whatever. And the bulk of the code for converting the intermediate representation is just contained in this file, C1 lir assembler AR64. We're just going to have a look at the code for generating a lir add. Okay, so this is it. We're entered with a tree. So we've got a lir code, which will be something like an add or multiply. We've got a left and right operand, destination operand, and then some general information about our code emitter, how we're generating the code, and something called pop-fdu stack. Pop-fdu stack isn't used in this. So on entry, it just tests if the left is a single CPU register, if the right is a single CPU register. If that's the case, then we generate a simple add W instruction, and then there's obviously cases for if the left and right are double operations. So very traditional, just sort of converting the tree into very simple assembler code. C2 compiler, okay, the bulk of the C2 compiler is contained in a single file, AR64.AD, the architecture description, which is about 12,000 lines long, which is not ideal. Pretty undocumented. The only documentation I found on it is this document here, dating from 1997. So if you want to know about it, it's a case of looking at either the x86 source or doing your own experiments. And what the architecture description file does is essentially does pattern matching from the sea of nodes that's generated by the C2 compiler to generate AR64 output, for example. This one is again just doing an add integer. So our pattern here is set dest add source 1, source 2. Very simple pattern. We have the instruction cost. It's going to be one cycle, we think. This for when we specify disassembly, it disassembles it as add W dest source 1, source 2. And then we have the actual encoding for that, which is just simply generate an add W instruction. And then we have this thing inspipe, which tells what pipeline class this instruction belongs to, so it can do pipeline scheduling. Okay, so that was a very simple one. Then you can generate more complex ones. So for example, this one is doing a division by 2. It looks nothing like a division by 2, but this is what the C2 mid-end generates when it sees divide by 2. In fact, it's a shift right followed by shift left followed by an add, which is what you have to do to handle the negative case when you're dividing by 2. Okay, so when we see this specific pattern coming out of the C2, we know it's just trying to do it 5 by 2. We know a better way to do that. We'll just generate this single instruction, add W dest source, shift right by 31. So we're just shifting the sign bit down to the bottom bit and then adding that in so that we handle the way negative numbers are divided by 2. And the instruction cost again is a single instruction cost. And the pipeline is just IANV register. So what the C2 compiler will do is it will match all the patterns and it will choose the pattern that has the lowest cost as being the best one. So you can tune your compiler to generate better instructions for specific places. So I mentioned the .AD file contains a pipeline description, and the pipeline consists of resources, pipeline stages, and pipeline classes. So resources are things that you might find at the bottom of your pipeline. So you've got a number of ALU units, you've got a multiply accumulate, you've got a divide unit, branch unit, load store, and you've got your neon or your simply unit. Pipeline description here, I've done a very simplified pipeline description. So it's just issue, you've got 2 execute stages, and you've got the result write stage. And following is an example of H who's over add ILU reg. So what's going to happen is single instruction is going to write the dest in EX2, so it actually writes it before the write stage. It's going to read source 1 and source 2 in EX1, and it can dual issue as either instruction 0 or instruction 1. So some instructions can only issue on a particular instruction decoder, so then you can model that here as well. Okay, it's going to use the ALU in EX2 stage. Another slide in between that. Okay, we'll just moving on to special tricks. So I think I mentioned this before actually, it's on-stack replacement. Compile and jump into hot method. So if you've got a big loop doing something complex lots of times, it initially executes in the template interpreter. Then it decides it's run enough times around this loop, they decide to compile that. And it compiles from the OSR point, which is the backwards branch, with the current locals as inputs. And then it swaps the interpreter train for the compiled train, so then just jumps straight from the interpreter into the compiled code. So you don't have to wait for the method to finish until the compiled code is executed. It may seem an obvious optimization, but the initial JIT didn't use this, and they performed very badly on some benchmarks, particularly things like caffeine mark, which just spent their time in loops, and essentially ended up running completely inside the interpreter. Deoptimisation. Yes. It's an interesting trick. Because it uses profiling with C1 and C2, it can detect when there are code paths that have never been executed. So what it does is it says, I'm not going to bother compiling that because I've seen it's never been executed, and just puts a trap there, which if that code is ever executed in the future, which might happen if it's an exception, what it's going to say is, when it hits that trap, I'm just going to throw away the compiled code and I'm going to go back to the interpreter. Another case that might happen is you have an unresolved class, okay? And when it hits that unresolved class for the first time, it will again just throw away the compile method and go back to the interpreter. Why would you ever want to do this? Well, what can happen is you can have code that executes in the startup state, and it does lots of loops in the startup state, and you say, great, I'm going to compile that. But then after its startup state, it changes its behavior and starts executing a different loop. But you've just optimized for its startup state, so you've misoptimized it. So by doing this, when it enters the second state of the code, by throwing the whole method away and recompiling it, you actually re-optimize it for its changed behavior. So you're adapting to the changing behavior of the code, which is a really neat trick that you can do. Okay. So obviously when it does this, it has to swap the compiled frame that it's got on the stack with the interpreter frame. It's even more complex if it's inline, because you've got several frames there. Restore all the locals and then jump back into the interpreter. Quite a complex piece of code. Satepoint checks. Okay, what are save points? Okay, well, the thing to understand is for garbage collection, you have to know where everything is. You have to know where every single object is. If you cannot map that, then you cannot safely do a garbage collection. This causes a problem when you've got compiled code, because objects may transiently be in registers, and you don't really have any way of knowing that. Okay, so what we have is well-defined save points, and they're usually at entry to a method, exit from a method, or at a backwards branch, where there is a map between the registers and the objects, so that the garbage collector can construct a map where all the objects are in the system. So if you want to do a garbage collection, you have to make sure that each thread is at a save point. Now the traditional way to do this was with checks, so it would load a flag to see does the garbage collector want me to move to a save point. If it did, then the compiled code would jump to the Satepoint code and would pull it at that point. That was very expensive. So an optimization to do this is we have a Satepoint pulling page, okay, which can be read protected. So when the garbage collector wants to do a garbage collection, it read protects that page, and then every thread that's running immediately hits that page, because it just does a load from that page at the end of each loop, and causes safety, and then the safety can cause it to enter the Satepoint code so that the garbage collection can complete safely. So we'll just look at some of the performance optimizations we've been working on over the past year. This is not a complete list, but it's just some of the more interesting ones. Okay, so we've implemented CRC using both SIMD instructions and the built-in CRC instructions, and we've done that because the CRC instructions are optional part of the architecture. So we've optimized it for both processes that have the CRC instruction. We've implemented AES intrinsics using the AR64 crypto instructions, and also SHA using SHA1 and SHA256. Strangely, the AR64 doesn't have an SHA512. I don't know why they haven't added that. Maybe they feel that's never going to be important. Currently, SHA512 isn't widely used, so SHA1 and SHA256 are the main ones that are used. But it is possible in the future that SHA512 could become widely used, especially if SHA256 was ever cracked. That they would immediately move to SHA512, which would be very unfortunate. The allocation prefetch optimization I mentioned earlier, where when we do an allocation, we just read using the prefetch instructions 3 cache lines into the allocated object to speed up subsequent performance. String intrinsics, so we've got support for the array equal operation, the encoding an ISO array. So Java, as you know, stores its characters 16-bit values. Obviously, when you're writing that out, you want to write it out as an ISO 8-bit string. So this is the method that handles that. And string index, which is widely used for search. Pipeline scheduling optimization, we've done that for in-order cores, so particularly for A53. Math exact intrinsics, okay, these are used for overflow detection. So normally to detect overflow, you have to compare the results, and if you're doing it in C or something like that, there's no way to access that. So this just provides access to the overflow flag so that we don't have to do additional checks. Obviously with multiply, because on AR64 the multiply instructions don't set the overflow flag, we have to do special coding for that, set in this case the 0 flag. And then there are some other small intrinsics and a few minor optimizations. The OpenJDK for integer division by 2, using attributes instead of moves for Satepoint calling, optimization of the CPU entry point, and optimization of addressing of card tables for garbage collection. Okay, so I mentioned the instruction selection versus pipeline scheduling. So we've 2 ways of selecting an instruction. Okay, you've got the instruction cost model, which is a basic instruction cost which C2 will look at when it matches patterns. Okay, and if there's multiple ways of matching a pattern, it will look at all of them and it will choose the one with the lowest cost. And we optimize that for out of order cores, so typically about A57. And then, yes, so this is just another example. So load B we assume has a cost of 4 because it's doing a memory access. So we've got a cost model which is general. It's not tuned to a specific implementation really. It's just a general cost model of roughly what uses instructions cost in terms of practical execution. In practice, there isn't going to be a benefit in tuning precisely for a specific architecture because there are limits on the choice of instructions. For whatever it is. And then for in-order cores, for example, 853, it's going to schedule using the pipeline class that we saw earlier. Yep.
So you mentioned that there's probably not too much benefit in optimizing for implementation, special or custom cores.
Yes. What I mean is, there are only a number of limited ways you can compile certain things. You know, if you're doing, for example, return A plus B, okay, in Java code. There's all you can do is load, add, store. So what I'm trying to say is that there's no point in tuning it too much because you find, well, it has to generate a certain set of instructions to do the operations. It doesn't have that much choice. Okay, does that make sense?
Right, but I mean, is there cases like you mentioned, like the divide by 2, you match that certain pattern,
Yes.
and then you emit the better set of assembly instructions.
Yes, and it will do that. But what we don't need to do is go through every microarchitecture and say, oh, well, on this microarchitecture, it will be issued in a particular stage, and it might take, one additional cycle for the result to be available. So we should put an instruction cost of 2. That's not relevant. It won't affect the code that's generated because all we're trying to do is differentiate between when you've got a better way of doing something, we just put a lower cost. So in the divide by 2, we just put a cost of 1 on that. So when it looks at divide by 2, we could do it 2 ways. We could do it using this combination of all the shifts, or we can do it using this single add. The instruction cost for the single add is 1. The instruction cost for doing it the other way is 3. Well, it's a no-brainer. It picks the add, okay? But it doesn't need to know what the exact microarchitecture cost is. Okay, it's a model basically.
Yeah.
It's not precise for the microarchitecture, but it doesn't need to be. It generates the correct code. Anyway, does that make sense? Or does that?
Yeah, but I'm just curious, like if there's certain scenarios where, like I think you mentioned the other day, the CRC instruction might take 3 cycles.
Yes.
What if that's just as an example?
Yeah.
What if that changes in a different implementation? And like, is there an option to select based on implementation, or is it doesn't give you that?
Not really. This is built into the compiler, so it has one cost model that must fit across all. So
Okay.
we've done that. In the case of CRC, because that's an intrinsic, obviously you can implement the intrinsic specifically for different architectures, and you can get to do it. But so
how much performance gain cost model for 857?
That's difficult to say, okay? Because we put the cost model in very early on, okay? We've never run it without the cost model. That makes sense. It's an intrinsic part of building a file. When you first write your architecture description file, you're going to put in the cost model so it can execute the instructions. So we might be able to do that by, say, setting everything to an instruction cost of 1. But I don't know what the